This is a material type technology that is something I only actually got into uh, because I wanted to make better internal combustion engines. So take this for what it's worth, all right? Uh, and I need to make it in mass cheaply because, of course, uh, production, manufacture, and expense cuts into everything. It was to be added into my anti-gyroscopic piston inline four, like the world's best. I named it that just because it's a clickbaity title more than anything. I don't know if it really is, but at the same time, it's pretty cool. But it's an individual like crank per each cylinder, and it has a let's see here, what was it? It is a 2-4-3-1. So it goes from the center to the rear, and then from the center to the front. And the reason why, because they fit in between each other, it basically makes sure that it doesn't need to worry about certain gyroscopic effects. It's crossplane because it's 2-4-3-1, 2-4-3-1, like 180. Now, the reason why I wanted to talk about that is because that would have to be a whole other video about how that kind of tends to get into for gearing, a crank pivot for bottom and top styles of valve covers, which aren't really valve covers, they're crank covers, they're crankcases now. I use air injectors and fuel injectors combined together, and I have rotating valves that use, again, they're just plates that are effectively just going to rotate that allow for the exhaust, so that way I don't have to worry about valve flow anymore. Now, the reason why I want to talk about extremely hard and thermally or thermo-insulative materials is because that is basically perfect for that kind of engine because I use a nitrogen filter, which means it's very, very hot, very high heat. And it's supposed to rev for a long time at very high RPM, which means they need to be very, very slick and they need to have very low heat loss. So, just the premise out of the way, I figured out that iron combined with, let's see here, I gotta get back into periodic table on this. It's been a while. Because iron nitrate, I use aluminum, but like iron nitrate is like kind of a thing that I'm using, but not really. Okay, like you can't really, like aluminum and iron don't want to mix. And if I'm using silicon, which is something that will mix with aluminum, then you can actually get somewhere with that, right? But not really because you need an intermediary element. And a lot of people are like, well, it's gonna be lithium, hydrogen, all this other. It's phosphorus. I use phosphorus. That's right. I use phosphorus. But see, there's a reason for that. All right. So if I effectively do like a powder coat of silicon with iron, and there's a little bit of carbon in there, but the carbon's going to disappear, right? So it's just because it's iron needs to have something that'll help it stick initially while we off gas it. So let's see here, because it's a nitrate, right? So it's a nitrate iron silicon phosphorus blend. You're gonna have to chill out, okay? But the carbon effectively gets off gas, and then the phosphorus gets pushed deeper in. It's a powder coat, and then we pressurize it under argon, bake it as per normal, and then we get it into a vacuum, right? During the powder coat baking, okay, all I'm doing is placing a bit of a current through it, like an electrostatic kind of current. and that helps with the off-gassing to the argon, but also adherence and phosphorus movement with silicon, aluminum, and nitrate iron, right? But it sets up a structure, chemical bond structure, that's a lattice that becomes more fullerene-like in a moment. Give me a second. You want to listen, trust me, because this is actually a thing that you can do. Okay? So hold on. Right. Now, during that vacuum, we're effectively hoping to pull a large amount of that carbon out using a electromagnetic and an basic charge variance, more or less. I mean that, like, it's a very weird thing to say, but it's like we pulse positive the block, and then we yank it to the negative with the help of electromagnets. Pulse, yank, kind of stuff. When it does that, it likes to compress, right? It basically helps move something away and then it condenses, right? Now, it's only meant to set up a structure. So then I'm getting out effectively a couple of 10-watt lasers, but there are two steady state types that are next to a middle one, and they're constantly firing, all right? But they're just 10 watts. Then there's a pulse one that's effectively like a million watt. But because of the way they're angled and the distance in a circle for each cylinder we're talking about here, along with the electromagnetic field that we have around, there's no pressure, I believe. Let's see here. Last time I checked, you just need like a basic electromagnetic. But anyways, they're going to reflect towards the center, and because it pulses, it creates like a pulse jet acoustic resonance. It collapses forward, it then reflects off, and then also hits the next reflect and also steady state laser. It produces a constant, insanely high wattage frequency that is very adept at going into picolength meters of accuracy, and in the I think it's in the billion or some crazy really high number, but it's also attosecond in terms of its firing effectively. But what that means is because the lattice structure is such that it is, and it pierces because of the steady state, and then the collapsing light photon wavelength goes inwards, it then vibrates and then shocks outwards, and it creates a internal fullerene that then has a fullerene ball around it that has structures aimed for, like a carbon onion ball, except it's very specific structures towards the edges of a uh, this one is a 5 and 6 combined for the inside, which is what the phosphorus, silicon, iron nitrate tends to bond pretty well together like that. And then it has a sticking out at the corners where that is as a covalent double bond that will then combine to a outer fullerene that's like an iron, silicon, nitrate, and aluminum blend that has a bunch of phosphorus that makes an insanely hard substance that bends just slightly. And I mean just slightly. Okay. But it's very hard and extraordinarily good at reflecting light. And will, in practically no way, absorb heat. It beats insulative materials we currently have by about 100 times, like our best that we've ever managed to figure out. It reflects IR, microwave, radio wave, a lot of natural light extraordinarily well, which is good. You're going to want that because that's really positive for an internal combustion engine, right? But it's like, I then got a bunch of diamond-like carbon, and it's another type of powder coat for the piston skirts and the piston head, right? But it's a little different because, again, they're aluminum, right? But I need them to bond, and there's not a lot of good ways to do that without a nitrate and silicon blend. But silicon nitrate is a really terrible kind of fucking thing to try and make, so I never really do it. So, but diamond-like carbon exists, and compressing it, while nice, isn't going to work. And so what I figured out was, with the silicon that's there, I'm able to create a bunch of fullerene carbon onion balls and monocrystalline and multiple polycrystalline monocrystalline structures that kind of intersect significantly in between each other with silicon and aluminum that fill in gaps. And so they're now effectively bonded to the aluminum. But the problem was that it's insanely highly conductive, but it's just as hard as what the pistons, I mean, the cylinder sidewalls are. But it's just as heat insulative. So it's really good electrically to a degree. Like, in fact, we have a way better conduct. Like copper is just as good. I'm just saying I don't have to make that. It, you know what I mean? So, but I'm gonna move on, okay? Because this will mean something. As heat from uh, the piston doesn't get absorbed, along with the cylinder sidewall, right? And well, then it also happens to reflect the vast majority of light that it's going to emit. So as it goes up towards top dead center, you do your standard spark and a little extra oxygen or whatever, and then you burn after top dead center to keep it, accelerating to gain and maintain pressure, right? The problem is that it likes to produce plasma because shock waves and light waves started creating cavitation events and then increased compressions and an ordering of shock wave based upon it's a cylinder, so the center, of course, gets hit, but then that center goes up and down. And so it would then create an acoustic resonance to a conductive material that would go to nitrogen that actually is below it that wants to go and have an extra electron, right? So it became ionic. So it came out as a plasma that goes to an ionic, and I would pulse it into. There's 4 turbines that would then combine from top and bottom into one major big boy turbine because each one of those cylinders effectively has an in between pivoting section and opposing counter rotating crank effectively. It goes to a main one that, for front and rear for you to combine it into your transmission and stuff, right? So it has basically no gyroscopic, sorry, issues. The problem is, like, most people don't really know that, like, 9,000 RPM for a motorcycle bike when you're trying to turn really helps you not suddenly fall flat. So when it's gone, all of a sudden it's like, oh, whoops, thunk, and then you fall. So that was my mistake. I thought people would kind of realize it's not just the wheels that keep you upright. Like, that gyroscopic effect does help make it tremendously easier on riders to learn how to actually ride that bike and not be terrified of falling over at high speeds just because, like, you don't have a gyroscopic effect. But anyways, that would then get combined. That's an accelerative process, but there's still carbon there, right? Well, it turns out carbon, when it's in a plasma state and it wants to combine with oxygen and, has the electron transfer, While it does that, you can separate carbon into a catch can, and that's like a ground state. And then I maintain more efficiency because there's an exothermic reactivity that's going to happen to the turbines. And I keep and maintain pressure and cooling too, because nitrogen keeps getting blasted in between, like the pulses between each power stroke. So 180 degrees every power stroke, even though it's not flat plane, it's cross plane. But that's a whole, because it doesn't accelerate for the harmonic, because of the way I basically did gearing essentially on that. So it's like, oh, it changes its gear ratio and applies it to the crank and the pivot differently. And it's a whole thing. But that also means that it's like, right, it accelerates when it needs to, something else is accelerating, and it decelerates and all of that. So it's all very perfectly balanced, right? But um, it's kind of like a turboprop. So like a compressor is getting sent through a nitrogen filter, but then that nitrogen's always getting put into turbines. It's helping cool the turbine, but in reality also it gets blasted from a 180, but then there's a 90 also, right? And that 90 is because the turbines, which are structural, so you're not getting rid of them from the exhaust manifold, are made to be a super turbo. And it dumps its extra past a point, like an MGUK, into the crank. And I use a thing that I talked about for two-stroke stuffing. I added him for a variable valve duration crank that I'm talking about for that gearing ratio. So it accelerates differently and decelerates differently, and it hangs at certain points differently. Instead of needing to pivot around, it can be quite a bit more up and down, like a rocker arm does. But that also means it rotates something differently, but then that's counter rotated and that's also added. So a bunch, like if I'm gonna have this amount of weight and I'm gonna have these amount of bearings and all that, I was like, well, this just makes more sense to do. It's effectively the same amount, but now it's effectively balanced in every conceivable manner that you can balance it. Anyways, same thing with the turbines, but that adds itself into the cranks. So as a result of it adding into the cranks, nitrogen pulse at it's around that 92 to 9800 RPM, where it'll suddenly start pushing a lot more of its power into the crank, and it'll be very consistent, steady power delivery. So it's like 100, 360-degree power delivery, like a electric motor, right? But below that, it has a weird power curve. So it'll go up and then it'll go down a little bit. And then there's this other power pulse of the nitrogen that like intersects, and then it'll go down and then the next 180. So every 90 degrees, I get a power pulse, or 360, like I have a V8. But I got 60% of, like, let's say I had 100%, and I was able to get 40% from the piston, and then there's 60% left over. Well, from that, the standard turbine, I should be getting only 40%, right? You know, a bunch of turbines, sure, whatever, but there's a limit there, right? But it's like I actually got 60% above that 40%. So I actually got more than 60% out of what was there. And it's like, why the fuck did I have that? I was looking, I was wondering where, and it's like, oh, I know why. Because there's an arc. The ionic then arcs as an electrical Z-pinch current at the end. And so as it would start expanding towards bottom dead center for it, it would then push it again with like a solenoid like linear acceleration. And then it would recombine into the turbine or super turbo part, right? The turbine. instead of having to burn more fuel, it just conserved it really, really hard. And that Z pinch would arc into the next, effectively reburn. But in so doing, it comes out as N2s, H2Os, and COs. But very few COs and CO2s. Most of the carbon's captured at 90+%. And it's like, you can't say that. It's like, no, I can say that because it's effectively a plasma, and I'm filtering it out as carbon, off, and I'm capturing that. But it undergoes a phase transition of H2O2, so hydrogen peroxide, because of the electrical current and pressures we're dealing with, and then it decomposes with NOs, nitrogen oxides, that explosively decompress and produce a lot of H2O, N2s, and O2s. Very few carbon dioxides effectively are remaining. It can't capture everything, but it's a lot, right? Cool stuff. The only reason why it works is because I have an insanely hard and insanely thermally insulative material. It's effectively non thermally conductive. Like as close as you could probably get, right? Without having a bunch of vacuums and a whole bunch of active, no, you stay warm over there kind of stuff going on, right? But the reason why it works is because of the inner fullerene and the structure, the compounds, meaning elements we're using. They reflect very well all of the light that we're talking about and are so hard and so unwilling to move that when they do, they actually make more light occur and resonantly reflect off as they expand from the initial burn. Now, if it wasn't for how conductive the damn shell of this thing is, electrically wise, it would never do this. And I mean that. Like, it would never do that. Then I got into, I need more friction reduction. I was like, well, I don't even need, why would I need piston rings now? I don't need piston rings. Like, I literally don't need piston rings. So I was like, all right. So I got into vacuum, superfluid, and magnetic bearings. So instead of magnetic fluid, a magnet's in a vacuum, nearby a pressurized hydraulic fluid that's a lubricant. But because it's near a vacuum, it changes its pressure and it becomes a superfluid that then has a vacuum that's just there for a magnet, and then a superfluid lubricant that's the bearing. So it's essentially as low friction as you can get. And I was thinking about it, I was testing it kind of in my mind because I'm pretty good at that stuff for logic and math and so on. And it's like, well, I started at 100,000 RPM, which isn't really the case, but it kind of is. Like I did do that in a vacuum of all things, right? But it's like, the whole thing, right? Because like that's usually how most physics tend to be done initially. But anyways, um, that turned into 100,000, which the material strength was able to handle. Blah blah blah. But that's a whole thing. Which is why I started there, because it's like, well, it could technically go to about 120, but it's going to slow down over time. So like, what's the distance? I mean, if we're going to get really hot, they're very high heat, right? Resistant, but they're also extraordinarily hard. And that's what I use for my bearings as my piston rings. I actually put this fluid with the magnet inside of the piston heads, and that's how I make my bearings now, as vacuum superfluid bearings with a magnet thing, because it's also in the cylinder side wall. So I was like, all right, Well, I've got the bearing, the main journal, and then I have the cylinder, right, sidewall, the piston skirt, and all that. I managed to go from 100,000 after an hour to effectively 999,987, roughly. I mean, there's a degree of variance after 5 tries based upon effectively noise control more than anything, like how you lift off the thing spinning it, how tenuous its grip was, how it's accelerated or decelerated after, stuff like that, right? So effectively a bunch of that, but it's like that's after an hour, and it's not 9 or 9, but that's yeah, it's the comma there. That's 99,000. Jeez, right? 99,000. And there's a decimal. Oh yeah, no, there's a decimal. Yeah, yeah. But it's like, huh? I had to check that. It's like, but the math checks out. Like for the heat, the basically loss of any friction is reduced because of the compounds that we're talking about and how hard they are, and the fact that they almost never touch. Like where they are touching is covered by a superfluid effectively. And that's great. Mostly because it means there's very low friction. So I was like, man, I want to make this fucking engine, right? This is what it kind of came across after a while, but it was really just because of how cheap it is to manufacture. It's effectively a couple of lasers, a little bit of heat, a little bit of powder coating, and then it's like a little bit of compression. So that, oh right, so the baking under the argon was at a kilopascal of pressure, 1 kilopascal of pressure in argon. That's it. And then there's a vacuum point for off gassing, right? So that's it. But anyways, that made the structure occur, if only because I was able to use those lasers, and I have to, of course, this one is like, well, yeah, no, I have a thing to go through the cylinder, but it's like, and they're firing it, many times, sure, and, in multiple spots, but I have to go down, and I have to do it on the way back up, I have to do it back down again, I have to turn it slowly, and so a lot of stuff is essentially a bunch of that over and over and over again, but it's actually fairly cheap. Like it's just gonna take about an hour per cylinder. So, that's like a 1 liter cylinder, bore stroke square, right? And you should probably figure that out. You should probably be able to figure that out if you know what that is, right? And that's an hour long for 4 of them. So that's 4 hours of treatment. But, considering that's not as bad as it could be, I feel like that's still worthwhile. You know what I mean? Um, but the thing is, uh, those are all, really good guesses, or whatever, right? Like that's how that works. Like the logic is sound, the peer review, all of that works, but most likely you're not someone that can easily just immediately do it, just like me, as well. I don't have the money, and most likely you don't either. So there's that. So uh you know that's kind of a thing, but the reason why I was talking about it is because I was watching a nuclear physicist reacts to, or explains and compares all Gen 4 reactor types. Alina Charasidou, or Sidao, or I'm sorry if I'm butchering your last name. Point is, uh, I was like, oh, that would be incredibly important for how like reactor types work, because it'd be about heat, and then I'd be able to contain it and then only have it come out where I need it to be. And then they're very hard, but then that can be an internal side structure with a, properly fitted outer structure that allows for it to still maintain its material strength for transferring heat to where it produces electricity, which most of mine tend to just turn into piezoelectrics. Like, I know this is going to sound stupid, but all of my designs are piezoelectric. They're like typically a vacuum Stirling engine radiator that's a piezoelectric. So if it vibrates and it moves, it produces 90% electricity for a given heat exchange event. And so then it becomes a big, big radiator instead of spinning turbines or something. It's like just radiator, just be big radiator, just super large radiator. And then it's like, well, that'll go into this one, to that one, to that one, to that one, to that one, until it's like, behold, my small little thing to a big, ginormous, huge. Jeez, that's a big radiator. It's a big boy, just up there. Is convection. It's effectively just convection. And the reason why I do that is because it's like, well, then that's buoyancy. By the time it cools off, it's like, well, that's a water battery. So like that'll come back down, and that's a bunch of instead of spinning. That's a type of resonance acoustic vibration with a little bit of like my bladeless turbines on my YouTube channel that are deeper in there, but it's effectively the same thing with a little bit of vacuum, and then it goes into the reservoir, and it continues producing a lot of electricity until it I guess has to be changed out because of well, no, I mean it works depending on what type of material you're using. Like the hardness of the material is just fine in terms of like supercritical fluids. It's not going to break down to that, which is good. But like it's great for piezoelectric surrounding, but like then it's more about the um vibrational aptitude, which means exchange. So it's like it's lightness and bending, and then the material that's there to exchange the heat has to be able to handle it well. And so while it's great for getting, heat to there, right, it's not as good for some of the stages, right, of heat exchange. Because it's literally insulative, so it's like the very opposite. But then it's like, yeah, but then you only wanted to exchange here anyways. And since during that exchange, that's the Stirling engine, but then it's also 90% efficient as a Stirling engine because that's the electrical conversion, and because I can surround it now by a heat insulative, highly conductive material, then I have the ability to effectively make a very high efficient, high heat nuclear reactor type of heat exchanger generator. And that's the reason why I kind of thought about it. Uh, is it triggered, like I was talking about it last night, but I didn't record it. Just because it was like, well, I didn't, whatever, nobody would believe me anyways. But who knows? Maybe this would be good for her or them, building nuclear reactors. Because then I tweeted about like how to make effectively a vacuum that if you properly protect yourself, like line and reduce radioactivity when you vaporize in a vacuum, and then layer deposit using ionic and Z pinch for electrodes. You can use that as a enrichment to 235 and 238 uraniums very easily with low amounts of energy required. But you can also add in structures of lower fissile material in between, and so you can bespoke make each rod and not be anywhere near it while it's doing that. But I also said that you can add in carbon or nickel, depending on how you want to do it. And so that can help reduce radioactivity to exact specifications that you're looking for. And then you can combine several of them to allow for a hybrid fast reactor, but also a slow reactor combo, right? That has a higher amount of surface area to extract heat from, which before is not necessarily something that people were able to do as well without a bunch of complicated blah 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 and high expense. So it's like, yeet, here's cheap as fuck, get her done. So that kind of thing. All right, I had to pause that and pee real fast. But it's like, all right, I wanted to talk about that because it's like that works, but it's mostly because I wanted to make spaceship microreactors or airship, vacuum airship. So like there's a vacuum inside there, it's very large, it's buoyant as a result. That's how buoyancy works. Right. But it's like, right, but now I have the ability to break down old spent rods, nuclear waste, and then refine it again using a little bit of electricity and solar, right? And then I have no waste until it's completely, totally used up. I have the ability to entirely extract all of the fuel and have no radioactivity as a result. It is 100% efficient and recyclable, which is the reason why I wanted it, because it's like, well, if I have to do a long duration space travel flight, I don't want nuclear waste. And I want this to extend its lifespan by a very large amount. Especially when it's like, well, if I'm traveling really fast, I have the ability to essentially utilize this to make small fusion types, particle accelerational fusion types that are nearby, or charged particle uh, charged particles hitting areas to heavy up effectively certain elements, right? Uh, because the faster you travel, the more neutrons hit you harder and more often. But it's like with this neutron electric motor that's on my YouTube channel, that means I have the ability to turn these spent fuels into something that will then fissile again and again and again with very little amounts of electricity until I effectively have a heavy hydrogen that makes it much easier for me to fuse and then eventually spit out as a quark and neutron and gluonic plasma with very low amounts of electricity used. So it extends the duration and the capture of neutron degradation to nil in terms of like, you know, that, but also duration of continual thrust as a 1G thruster for a very, very long duration. As long as I can get to a point where I have the ability to absorb a little bit from a planet's atmosphere, gas giant or whatever, then I have the ability as well to try and fuse a little bit more with higher degrees of neutron and heat, and then start effectively a fusion to fissile back to fusion, but it's really not fusion. It's really actually extra hot, more easily fissilable material, right? And the extra energy, of course, is, well, the fact that you have neutrons around you and you're going really, really fast. Kind of like exothermic energy. Like, how'd you get 60% basically above the 60% or whatever? Like, yeah. So a good way to put it would be like, let's say I got 60% from the internal combustion engine, and there's 40% left over. Well, I got 60% from that 40%. So where did that 20% come from? And it's like, well, because it's exothermic. It's like, oh, I have this electron movement that wants to do something, right? And so electrons then go burr, more excitey, thermal, right? And that makes more pressure, which is good. I recapture it, right? And of course, there's got to be a loss, but it's like, yeah, no, there is. It's carbon. I have carbon as a loss. But it's like, I can reburn carbon. There's still an atmosphere here. And I can put in water. And then if I have a bunch of oxygen, I put a little bit of water in there. Now, granted, most of it didn't heat up, in fact, at all. So I have almost no need to water cool or liquid cool or even air cool this, even though it's extraordinarily hot, which is nice. But it's like, all right, so, but now it has carbon in it. The steam, as it's in a low pressure environment, but it's there, right, because it vaporizes. But it has a bunch of oxygen and a bunch of carbon now in it. But it's like, okay, that's cool, but then it recompresses, and it's like, yep, with oxygen around that I can fire with the air injector. So just before, which is the reverse of compression ignition, for fuel being injected, it's air, oxygen. So it goes bang, and it goes as it continues, produces a lot of steam, but then it's so hot and it's rapidly accelerating away. And because it's polar, as it decompresses, because you probably already knew about that, it then likes to yank out a lot of the carbon bonds to oxygen and starts the cycle again as another Z-pinch as it plasmifies itself and then wants to recombine. It only works because of the materials I'm using. Like literally the materials make that effective. If it wasn't as insulative as it is, and if it wasn't as reflective to those given light expressions, meaning large electron orbit movement that produces very, very large amounts of bright light that normally gets lost and doesn't get continued to be captured into the system as it expands, which that's another part of this. It doesn't have a way to like reduce its expansion, right? So it like rapidly expands and changes its compression rates. But then it also happens to have an acoustic resonance through that. Anyways, point is a bunch of stuff that's blah 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 stuff to others, but what it means is it likes to decompose more easily and turns into like a fuel cell as it does so. That'll then recombine. And I get the carbon back, right? But in so doing, I maintain most, and in fact, a little extra, because it's not like the turbines aren't made of that, you know what I mean? So, of that electricity and heat. And so electricity has to go somewhere, right? But it's like, yeah, for the next spark ignition. So, anyways, I just wanted to talk about it because it's like, well, that's essentially what I'm going to be doing for nuclear ignition fusion styles. I'm using a bunch of extra neutrons, like it's an atmosphere, and a bunch of light that I talk about in that, that's able to be concentrated and used during those processes to increase the likelihood chance of fissile infusion that can be tailored. But it also means that I'm getting that electricity sent out and extra heat and pressure sent out as thrust. High Q value thrust, but that also extends the duration of 1G thrust to a stupid amount. Once you hit near light speed, it becomes a bit of an issue. You know what I mean? Like, we all like to think about, like, we can continuously 1G thrust, but then when the moment you turn into a person that's at near light speed and you're just throwing more mass, but about the same speed to continue a 1G thrust, it gets real dicey. So, I tend to not, like, dwell too much on that, but, like, for planetary, in our solar system stuff, it makes sense. But for interstellar, it doesn't. because you need to move faster than light if you really want to do that. Which I have several different things on my YouTube channel about that. So I'm going to move on. But the reason why I was thinking about it is because it's like, well, now I don't have any real like loss. Like it's basically fused or as a result of it turning into heavy hydrogen or very close to heavy and ready to fuse material that just get blasted out. Right. But I then have the ability to enrich hydrogen that we can capture as we go through space or fly by Jupiter or Saturn or wherever you're going. So, but it's also really good for people on just regular Earth here because it's like, well, now there's basically no radioactivity, and a microreactor can be made to be like 100-year long reactor that produces um, terawatt hours over its lifetime, which is great. It's really good. It's usually a good thing, typically for most people. Usually, it's a cause for celebration. So, good old Merry Christmas, Right. So I continued watching a little bit more and I'm seeing a lot of like everything basically just destroys all of the things. It's corrosive. Everything is corrosive. And I'm like, oh yeah, no, I forgot about that. I just thought that they already had materials for this. Um yeah, okay, so hydrochloric acid is very easily able to strip the inner of the cylinder sidewalls material, and in order to do what I'm talking about for the thermal resistance and everything, it is uh, uh between zero point 0.1 and 0.21 millimeters thickness, and it does all of that. So uh the problem, however, is if you spit on it and there was a little bit of hydrochloric acid, that would be enough to destroy the coating. But it's stupendously unreactive to practically everything else. But it's also effectively ridiculous in practically all ways because it's highly thermally insulative. Great for transferring, but other than that, it's like, well, get out of here. You know what I mean? Like, who gives a shit at all? Nice, neat, but like, who cares? They're like, yeah, yeah, no, I feel you on that. Um, I mean, most of my materials for heat transfer that are highly unreactive really depend heavily on what it is that we're dealing with. Like chlorine and fluorine that she was talking about have always consistently been the same ones. Which instead of plastic, we usually do um, not zirconium. You do a lithium and fucking what is that? Give me the periodic table elements. Give me that, you damn bastard. See here. Selenium, and then a fucking where is it? It's over here. No, you can't do vanadium. Vanadium would be amazing, but it's super not great. It loves to be carcinogenic if you ever fuck it up. So selenium and tin with a nitride of tin will work. But that one's, let's see here. This is a L2 SE1. If you can get away with it, I doubt you could. So it'd be an SE5 with a N4. No, not N4. N6 with a T. Was it 10 again? God damn it, you bastard. No, SN. That's what it is. Right, SN 14. Yeah, it's mostly 10. But here's the thing. It's a multiple double bond that effectively has nucleuses inside of itself, which isn't really true. I'm just letting people know, but it looks very much like they are. Like kiss. Like, just get. But uh those are really, really uh, low production materials. So, like, those are the majority of the ones that I'm aware of. They are all tin based and basically do that well, and they're polymerized, uh, which isn't really truly the case, but they call it polymerization. I'm like, that's not polymerized, that's a crystalline structure. How is that polymerization? But whatever for whoever's selling extraordinarily expensive material. Uh, so good luck on that one. Um, and then it's like, right, uh, freaking fluorine, chlorine is annoying. Most of the time, people are like, "Well, why can't I use like this plastic?" And it's like because it's poor heat transfer and it breaks down under the heat and pressure. Like, you know what I mean? So you can't really. But if you do want to, you end up using a hydrogen, oxygen, aluminum, cobalt, and carbon blend, which is usually H9. Let's see here, O fucking 7 C3 and or CO3 and C. All right, I forgot the aluminum. Fuck, that'd be aluminum. Freaking what was that again? 8, I think. Yeah, 8. Aluminum 8, CO3, C, uh, fucking 5. And that should effectively give you uh, a ceramic that is extraordinarily efficient and effective at not having issues with fluorine or chlorine. But water touches it and it will dissolve it easily. Like, it'll dissolve in air above a certain humidity, which is like I think 25%. So fucking careful. Lead, I love the lead thing. I was looking at that and I was like, oh, though that's interesting. Huh, that could be highly useful. What kind of like, bismuth is really nice. I love using bismuth and tin. Antimony and bismuth together with a combo of fucking tin is extraordinarily good at being able to be conductive and is insanely efficient at certain types of neutron detection as a result. We actually use it for that. But that also means it has a very high likelihood of reflection of neutrons and capture of electromagnetic fields um, that are converted. So it's like, see, neutrons produce electricity, but then it also creates a current, which of course there's a Z pinch, but then also it has to spread somewhere to do that. And so it produces a collapse field because, of course, the convection currents of this material are what they are. So alignment happens, it acts like cables in the convection currents that then also have arcing Z current pinches from the neutrons, which means they'll produce electromagnetic fields that cause a turn. So they'll spin, they'll rotate, and then they'll repulse and then also attract towards each other. But uh, if you happen to be good at pulsing electricity into it the right way, then you actually capture that as a charge field dissipation and you get more electricity from it. And so the neutrons give you direct electrical signal. And if you put it in a vacuum, you're even better at it because you need fewer hops through this dense material, but it acts when it's under a super critical pressure point for its heat. It then makes a very highly conductive material that's extraordinarily good at um, effectively acting like, instead of a superconductor, um, uh, uh, it's like the opposite, um, and for like a superconducting magnet. So it's like a superconductor is really good, but it doesn't produce a magnetic field. But a superconducting magnet is like the opposite. It transfers immediately electricity to magnetic, right? And so it'll take magnetic and then transfer it into electricity. And so it pulses while it does that, while it also produces a buoyancy that then collapses as you take the electricity out. And so that's like a distill method, but also that means you get an acoustic resonance and it's still hot, but it'll fall back down. And because it's so heavy, you get a big heat battery. Like you can start taking some of the heat out, but you can also get the acoustic resonance heat exchanger, which is nice, or just a turbine. So to put it in perspective, I was like, well, turbine still works. Just a little FYI there. You know, I mean, it's pretty hot. And these are really non-corrosive materials I'm talking about. So they'll probably work. I'm just thinking here they might work. You know, that kind of thing. So, all right, listen to the rest of them for helium and the supercritical water. It's kind of rough, actually. I got through it, or I was going through it. Not her video. Her video was great. Um, my mind started drifting into like that uh-oh space. It's an uh-oh space. Not because there's multiple solutions that are great, but because there's an inherent fucking problem and flaw that I'm seeing that nobody's talking about. That's bothering me, like a tremendously significant amount. Um, Again, I'm not a nuclear physicist. I'm not, but it's like, is anybody talking about the fact that we're effectively making sure to break apart something, and we're going to transfer that to something else, um, which destroys our coolant over time, which we're all okay with like coolant needing to be changed in our engines and it's slowly degrading our coolant lines and everything on an engine or whatever, right? But like we haven't mastered neutron conversion. Like we know that as a radiation type that is released thanks to vibrational field instability collapses inside of the thermal momentum moments of quantum probability. Okay, better way to put this. Neutron go birdie burr, and then it technically makes this other neutron exist temporarily, and then because it moved away from it, it then went, I guess I am a thing, and then suddenly happened. and then it yeeted itself off somewhere else. Is effectively what it really is, yeah. Even though we talk about it like, no, 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 there's this number of neutrons in the nucleus, and then this one decided to leave. But in reality, that's not really what's going on. Like, that's a part of it, sure. It is. But it's not like the truth. All right, like quantum probability shows off a wave function that does not allow for neutrons to do that with the number of neutrons that should not exist after a very, very, very short period of time. So for thermal excitation, it's creating neutrons. Right? And that's what my big issue turned into. I was like, wait a second, do they have information on this? Quantum probability should suggest that the wave function shouldn't really produce that unless we know what the conversion field is that it ultimately is going through. It's creating a virtual that's solidifying into a real. And how is it doing that? Like, if we were able to place with inside, like the vapor thing that I'm talking about, a surrounding material that is there ready to effectively, with corrected electromagnetic and electrostatic forces, we could theoretically have it turn into direct electricity instead, and no longer need a transfer, which is conversion, by the way. So, like this neutron and this thermal movement, because it has to vibrate to do that, there's a pressure here, and then it makes that neutron, get yeeted, right? And that's what causes vibrational movement, which is what we try and capture as thermal, right? The more we capture it, the better we capture it, the slower those neutrons actually fire. Even though we call them fast neutron reactors, we're capturing enough heat that means we don't get that efficiency, right? But what if we didn't need to capture heat? What if at that moment during creation of a neutron, we changed its probability by making it convert to an electron now? Or a style of electron that's more heavy, like it has more quarks that make it more heavy. Not neutral, it's still an electron, but it's heavier, right? Like, what if we were to do that instead? Um, because that might make a much higher degree of efficiency for our nuclear reactors. Just because that means I can scale it down to nano sizes of material with my vapor deposition process that I tweeted about, which is it's literally a vapor chamber, and then you run current through it that heats it up, it turns it into a vapor. But also we're making an electrostatic and ionic style of deposition that also gets a Z pinch. So what a Z pinch is, we'll run a current through, and if you pulse it the right way and use some laser light, okay, then it separates heavier isotopes to of course the lighter isotopes, right? Which is good, okay, but it comes at the cost of a lot of neutrons. It can be, if done incorrectly, it's actually really safe. Like it's the safer way, but if done incorrectly, it's really unsafe. Okay, like you'll suddenly have a massive pile of insanely pure, highly enriched heavy isotopic uranium, which you don't want. Usually, I would imagine, right? So, like, we're talking milligrams to micrograms deposited into very specific, kind of like a substrate material for like a silicon wafer. And if I can do that, then I have the ability to force with light and electromagnetic field and some electrostatic, but you really only need electromagnetic and electrostatic, which is charge difference for electrostatic, so positive, negative, and electromagnetic is just fields, which means coils. It's like, then that means I can potentiate the neutron change to an electron and it captures during a tunnel event. So I'll get more electrons because it's a field that's there that then suddenly gets uh, interacted and interfered with by that and instead makes a bunch of electrons, right? But a little bit of light goes a long way with that. It makes it more ordered and more likely, okay? Which is great, but uh, of course, there's no real current, even bleeding edge or waiting to come out articles that I'm aware of that suggest that this is possible. Even though the math and physics says it's possible, but we don't have any practical examples as of yet. So that's nice, but it's so experimental, it's concept experimental, which is great, but all of it should check out. Like, it checks, the logic checks out, right? But how long do they last? Right? Like, that's my thought. Like, we're talking about a substrate material that is pretty much going to be some amount of silicon. There's going to be some amount of silicon there. There's going to be some carbon, copper, and um, instead of like silicon carbide, it's like graphite or carbon wafer kind of stuff, right? Layer deposited stuff, but also copper, which, like, that's to really insulate it. But like most of it's just going to be like a copper silicon blend with a, I'd imagine we would need like maybe not a lithium, like fluorine would be really nice if I could do it, because that increases the likelihood chance of getting that electron to be pulled from charge differences passively. And then I can run, like, I need more electrons, current through it, right? And then transfer that, and that helps keep electrons flowing. Now, the half-life, of course, like, based upon quantum probability, right? But this would change that half-life. A good way to put it would be it would keep itself around longer, right? Because instead of allowing for the neutron to get so excited that it will actually finally leave, I'm able to kind of keep it in for longer, right? And it doesn't have any radioactivity. It is inherently safe by design. It has no more than ambient, hopefully. Again, no practical examples, but it should get to that point, by design. But we're talking a chip now that you could put into your computer that could run a computer off of that chip, right? It could do a few kilowatt hours, if it was dense enough, and that's the piezoelectric heat exchange, right? To like a light based. So that's what but the light would then get reflected and sent back fiber optically into the light that you're going to use to kind of more order it as a chip. That becomes a resonance phononic design that creates the piezoelectric, but also just straight electricity. Now, eventually, the uranium and more will go away into a split, right? but it'll take longer now, and it's more efficient capture, more total capture, because we're capturing light into direct electricity, and direct electricity for every neutron, which neutrons are the majority of what it is, and we don't capture that. We have to do the dirty thermal. You know what I mean? Like the vibrations, and that's not exactly as easy as if I could just get a direct one-to-one. Like direct one-to-one means fewer conversions, means higher efficiency, better Q values, longer lasting, just outright better. So that's what my big issue was. Uh, uh-oh. But like, here's my extremely hard and thermally insulative, which is perfect actually for this, because I have a thermally insulative, but I have a very high electrically conductive material that I can use with a thermally and very low electrically conductive, very insulative both ways material that I can surround, and it reflects a lot of the light that I need to be reflected, and I can make fiber optics that are perfect for this. So I could get way more electricity efficiently. I still do need to have some degree of vibration, so that means, well, that's light though, and that's interference. So like that's like the acoustic resonance and wavelength. So like as it moves through, that's a wavelength interference for like, longer to a shorter to a middle that collapses and constantly vibrates, which is great, but like that needs to be attached to a mass value, which would be the piezoelectric crystals, which would allow for that to capture. So given light, that's like an optical tweezer, but it's inertial optical tweezer that is a vibrational acoustic resonance, which increases my capture or light admittance to electricity while still allowing for the proper amount of light to order it at very, very high wattage, constant pulses that are like spike waves, which is what I was talking about earlier for that material. So like it creates these pulsing spike waves that bounce back and forth and creates a pretty consistent pulse. Stream spike wave. So it's like a constant spike wave stream that hits all the time in these really, really fast pulses, but it's technically like more of a constant stream wavelength that it never really notices for its relative perspective that I'm hitting it with a bunch of pulses because it doesn't know any better, right? But for this, that's perfect as well because that actually makes a lot more electricity generated, and I need a lot less light to do it. To make my chip it'd be a pico reactor. Yeah, this would be like a pico reactor instead of like a, you know, really, really small nano. This, because that's like you can get it into your car, right? Like a pico then turns into this is on a chip, and I could power your car with it. Like it went from like, man, I can get it to I could do way more than that. I could do genuinely a pico reactor that does hundreds of kilowatt hours, really, a second. I don't know if I have the connections for it, mostly just because it's like, well, yeah, no, this is really thermally conductive in no way, right? But it's really electrically conductive, right? But that doesn't necessarily mean it's a superconductor. But it's like, yeah, but I actually have something that's similar to that. It uses impedance and resistance, which you still have to match. By the way, I never said this on that video earlier. It's the neutron like motor one that goes over that like later on, but it's also earlier in my video channel, my YouTube channel, right? But uh, it uses a collapsing wave function resonance for electron movement. and then it also heads towards the center, that then heads backwards towards where it entered on the outside, and then goes from the center core towards the outside, and then it balances itself out. And I used a bunch of pulses. Anyways, point is, that is a really long video. It seems like I just turned into a storyteller at the end. It's actually really just like a possible future reality thing, given all the right scenario, blah, 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 blah. Moving on. Like, I know, like, what? It's like, that, just move on from that. It turns into a DC that's phased properly with a given type of sideways, vertical, and a diagonal sine wave, right? That's pulsed in a fashion that is extraordinarily fast, but then also uses a medium and a larger wavelength that passes through the outside, that then heads towards the center, that balances off from the outer core resonance to the inner core resonance, which produces a separation collapse field effectively. Like, they repulse each other, and then they actually spin that energy back into like a DC current, except it's always flowing as a recirculative flowing design, an acoustic resonance. But I use that as a thermal momenta information transfer resonance. It's quantum resonance momenta, thing. Anyways, point is, it means that it turns resistance into a near super. It's not a superconductor because it doesn't drop its resistance. It just transfers the same electrons through. So the same amount of electrons go in, and then the other side you get nearly, like, very, very close to 100% the same amount of electrons out. There is no conversion to electromagnetic fields or heat or anything like that. So, but that's not a superconductor. You see, a superconductor doesn't have resistance. This has resistance. You could still measure the resistance. That's why I said that you need to impedance match for this. You still need to do that. But you do get away with not needing to care about it once you impedance match, and you have to do the right kind of like connector type that goes around and towards the center, and then there's at the tip it produces a bunch of these field types. And so, like, you need to have a connector that goes around it, and then a connector that touches the right way, and then these little electromagnetic coils there, and they send impulse from outside in, or outside, side of that, and then they draw inwards, and then that like creates the next resonance skip, Wi-Fi hop, whatever you want to call it, right? For the tube. But it makes it extraordinarily efficient as a result. I don't get heat losses, and I don't get electromagnetic field losses, which is great. But it still has resistance. It's basically the opposite of a superconductor. It's like a superconductor has no resistance, but all the electrons are great, right? Except, not really. Like, you lose electrons during it that are more than I do, and you also have a limit because that resistance is still technically there, producing enough heat that it'll eventually no longer become a superconductor. And that means you need to use pressure to effectively get around it, right? But for me, I go, yeah, I don't care about any of that exawatt hours a second through this tiny, tiny, little, tiny, tiny gauge of wire. Like, go screw yourself. I don't care. I need exawatt hours now. My lightsaber duel is coming soon. Anybody who's talked about it, they're like, yada watts and all this to make this lightsaber with this battery. I'm like, okay, Star Wars with your solid light. Damn it. I would like to. How do I do that? Let's start with the battery first. I need way higher efficiencies if I'm going to transfer anything like that. What are these wires? What are they using for wires? So I was like, all right, so acoustic resonance properties now mean that I can do that, which is effectively what that is. But also, it's not using the quantum whatever thing that they're trying to create for a version of like this stupid. It's not the same effectively. Like like this, what is it? I forget what it is. Like a waterfall. It's not a waterfall. No, they describe it some fucking thing, but it's like no, the electron orbity blah 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 ten of it, and I'm like yeah, huh, yeah, huh. Similar but not the same in the slightest. Like this quantum phenomena, and I was like, well, it's not doing that. I don't care what the hell you fucking think. It's not. That's not the phenomenon. I already know what that phenomenon is. Anyways, point is, you'd have to look that up for superconductor materials and like how they're trying to figure out this other like resonance thing. But it's like, yeah, except yours is essentially a what did they fucking go with? Some fucking not a virtual. I forgot what it was. It was like a ghost particle or some shit that produces a field collapse into a extra electron that then moves the other probability of its electron orbit to being more likely to be over here, and then it then bunches and changes its phase and shape of the electron orbit to allow for it to be more superconducting as a result. Meanwhile, mine's like, nah, I don't care what the fuck your stupid phase is or what you're doing. Just go over there. Just spinaroo, man, and skip a doo dah, effectively. It's literally, it's like spin, a line during a spin, collapse as to I can't exist here because, dude, there's already one me here. And so now I'm gonna go yeet myself in tunnel probability over here on the other side. Except no, no, no. Guess the fuck what? Yeah, I'm already over there, so I guess I might as well go over here because it says I'm not over there now. And so then I oscillate. Tunneling. It's all about tunneling for me through electron orbits, which are way easier to do. Except you don't really need to do that because if you look like instead of each individual electron orbit, because that's annoying as fuck, you create packets, right? Little like big, groups of trillions upon trillions of atoms, and like they'll align like this, and then that effectively means they'll intersect and allow for transfer of electrons in those moments as a tunnel effect. But then they also create like an up and down rotating electromagnetic field that is a Lemke force instead of a Lorentz force because it's not electromagnetic and it's not conservation of momentum. Instead, it turns into a not repulsive, a electrostatic, like attractive. But when they have a core, then that attractive turns into a skip and spin out. So like they go near each other, and then it's like a big gravitational sort of like extra slingshot speed up, and then they dissipate upwards, and so they'll create like a that attractive force that was repulsive to them then repulses back in on the next uh, tunnel. And so what that means is on the up and down that squeezes them, and then it likes to tunnel more probabilistically towards the next area that you want it to instead of heading backwards as a resistive force. But it also dumps that energy back in as the electrons ready to tunnel next time. Okay. But it means I also have a battery as a cable. So like the cable becomes like a battery. Like you have to like acoustic resonate the right way. But it's like, yeah, but a cable is a battery when you have an AC or DC. Like there's always a certain amount of electrons inside of it anyway. So I don't see what the problem is. But the best part for me was it sped up from 60% to 99% speed of light. Yeah, so it's like 60% speed of light through copper, Now it's 99% speed of light, and I can go way faster because then I started using it for silicon chips, and I changed gate styles by pulsing it the right way with those types of phasing types as a DC. And I used an AC DC phasing type that would allow for me to increase the amount of clock cycles I could achieve, but also the amount of calculations that I could do for any given transistor gate type. So both ways they would work, but also I could change where and how they worked, which meant I could dynamically load them for any type of transisting and processing I wanted. And then I ended up at this other place for a dimensional compression algorithm. So it's like a zero part of this, storage and cell, like a cell, like a chiplet that has a little cell for a 0 or 1, right? It's there or it's not. Cool, right? Except if you store a little bit of information over here, it's like, that but that 0 is really actually a 1 as well, right? Okay, right? And that's cool, but it's like, no, no, no. If I dimension this the right way, which means a little bit more, initial memory sacrifice, I get a multiple dimension. This is a 0 1 0 0 1 0 0 1 1 1 0 0 0 1 1 1 1 0 0 0 1. But it relates to this, that, this, that, this, that, this, this, that, this, that, and this to this, that, you know what I mean? Like a lot of that. And so like I basically ultra hardcore compressed a massive docellion byte file that I actually streamed over to YouTube. But it like, no, 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 he's just doing regular things for a year. I'm like, yeah, no, I am for sure, winkety. But if they ever actually bothered to watch, it would be like, no, it's playing real time still. I thought I was able to go backwards. And it's like, yes, compress it to only 600 docellion bytes or something. And it's like, but that's actually not the truth because each 1,200 something docellion bytes, right, was actually compressed itself too, because I had 5 orders of magnitude of that. So that means I had the docellion byte, the 1,200 something docellion bytes, but I had that then times 10, and then I had to add that in, then I had to times that by 10, then I had to add that in, and I did that 5 times. And then I did that 3 times. Three times. That's right. For the total of that experiment. And it was like, if they were to ever get this massively huge file completely, uncompressed, it then has like total loss, pure information as the next full uncompressed state it was. But it's also, so 1,200 something docellion bytes, 5 orders of magnitude like that. So you take the docellion, then you multiply by 10. And that's your first one, first order of magnitude. Then you take that one, that number, and then you multiply it by 10, and then you add it together. And then you do it again, and you do it again, and you do it again, and then you do it 3 times for a total of like, well, there's a pattern here of 5 orders of magnitude for 15, really, kind of. But like, it definitely checks out as to being this is a thing that's going on for the graphing of the data. And like, that's the full actual total number of bytes. Because it was like, well, I've got like this billion fucking like little tiny these copper cable, all this stuff running 10 trillion. It's 1 trillion really, but that's a constant. Like, hey, this is what it should be for whatever, and then this is to check it against, right? Which is how I arrived to nonillions, because like the nonillions makes sense because that's 9, and then 500 is divisible. 500 nonillion is divisible by 9 trillion. And so I did that for those many number of bytes, which is the true lossless information. But long short story, some dude actually wanted the full total information. But it's like, if I know that with my given thermodynamic, fluid dynamic, quantum physics theories, like I run the calculations for that, which I didn't have the ability to do unless I could get the whole thing and be able to burn through that and brute force calculate work. I was then able to prove whether or not my math checked out. Because the only way it could work that way is if I had that many numbers of orders of magnitude being consistently like this, and it would fit the puzzle pieces of math that I had put together. Which meant I now proved my math is correct and all of your theories are incorrect, and these are the theories that were correct. Fuck you, I got laws of the quantum variety. That's what I did it for. That's literally what I did it for. I was like, come on, get the big, huge, massive storage thing. Do it. Come on. Get the big, huge storage server. Should I even know how many bytes that is, to be fair? Because it's like, well, docellion's a really large number. It's the one above nonillion? Times 10, you say? Which is times 10 to that number again, you say? 5 times? And then 3 times that number, because that's how many you did. Ha! No! Meanwhile, YouTube gave them the uncompressed kind of thing. Not really though. Like I gave them like my compressed one, and then they wanted to check it to like effectively the only real lossless recording that there really was. But it's like I basically kind of wormed and trojaned the input internet data. So like internet goes in like this, right? This is an IP packet, doesn't matter, right? Like to most people, right? But it's like I have to make multiple copies, send them out, and effectively have them all check against the same one that's being sent ahead of time, and then this should be the error correcting, right? But it's error correcting multiple times. But in so doing error correcting, if it checks out, it's now a hatch program that then makes it such that it comes out as exactingly this binary, but in so doing, it gets for their program to see what it is as this magical. It's totally, definitely the real. You're seeing me stream for sure information. And that's how I store. But to be fair, like a docellion bytes, 600 something, seems to make sense when it's like you've been streaming straight 24/7 for a year. It's like, yeah, oh, for sure, oh, yeah, wink. But they're like, I'm catching on to you. There's no fucking way. So I was like, I'm gonna input some streams real fast to make sure this will come out the way I want it to them. And so they were able to get exactingly the correct information that will break out uncompressed as the full 1000 whatever docillion bytes. But then it's like, then that gets uncompressed to the full 5 orders of magnitude times 3 that really was, of full raw binary data, like uber raw, like just raw as fuck data, right? Like everything that I could give them. Meanwhile, Google and YouTube were like, grrr. didn't have the internet upload speed. And I was like, behold, my fiber optic multiple phaser laser thing. And they have big multiple, like 7 beach balls, like one in the center and then 6 on around the outside core that they stuck to effectively a server of theirs. And they're like, I can't match that. Meanwhile, we have a 1,200 something docellion bytes a second cable that went into every one of their freaking storage servers. Yeah, that's why it was so big, but it's like all of that to make sure it could buffer and then properly offload it. And which meant it could do an actual docellion bytes, a second, right? The over 1,000, right? But Google was like, and YouTube had no fucking ability to do it. Don't tell them that you were exabytes a second, which is still really impressive, but still, that's not the same. It's not the same. It's insanely impressive, but still, that's the scale it was at. And they're like, well, it'll be done in a day. And they were kind of sad about it because they set up all of this for what it was worth. But like every one of those things then turned into like, well, we have to scrub through all the raw data. And I'm like, yes, I'm going to use this briefly with my own like little chip thing and all this and my computer really. And I'm going to prove my fucking laws in quantum physics. As a whole ridiculously large sum of data as it is. It's like, yes, yes, I know that you did this orders of magnitude, which apparently you only need like a couple billion, and I didn't know that. So I went so above and beyond. It's the equivalent of wham for consistency. Here's my big data wing. Here's my honka beluga whale dick of a data wing. Look who got the biggest data pool set ever. But those are many, many, many numbers of observations, billions of pages long of these nines, very, very close to exacting the same amount. So it's like what that means is for the given calculations for the noise that you could see in the area in terms of neutrons, electromagnetic, charge, nuclear forces, gravity, thermodynamic, and so on. I was able to literally brute force and hone into extraordinarily precise measurements of exacting precision, consistency, and accuracy of what it is our quantum physics truly are. But that's because it went on for 3 months at a time to get to the 5 orders of magnitude nonillions at 500 nonillions, running 24/7 straight. But that also means it's like, well, for this given year and this given area and blah 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 for a year, and when it's not doing it, blah blah stuff, it effectively means I can calculate for every given possible influence and interaction. Chaos theory mathematics be fucking damned, bitch. You're mine. There's only a set number of possibilities that will ever fucking work for this. And I brute forced it. Which meant, behold, my laws of quantum physics. But, that's another part that I didn't talk about. But you do have to impedance match, and you do have to remember your Ohm's laws. Effectively, electrical engineering didn't go anywhere. You still have to do all of that. And so there's that, like, you're not gonna get away with it, like, you could still, you know, have a resistance, non-match all that, but, like, it's not gonna work as efficiently. It's what it is. See, like, you get real particular about the sizes and all that of the gauge of wires and whatnot, and impedance like, you get real particular very quickly because it's like, "Yeah, but that's, like, so much loss. That's like 10%. That used to be good. Not anymore. We're talking about this is over the course of 12,000 miles of distance. I'm losing 10%." Well, we would have been in awe, like, "Oh, that's so good." Meanwhile, I need my 99.9999999 whatever amount of efficiency it is. Over that distance. You don't understand, and I need these exawatt hours in this thin fucking tiny cable. I need this. You don't get it. Ugh, the customer's always right. Remember, engineers. Who forgot the right size cable you take? Who forgot the fucking home slot? Who forgot the Who forgot who's forgotten the resist impedance match? Who forgot that? It's 12,000 miles. It's 12,000 miles. I have to check all of the. This pain is a good pretty penny. This is a tiny thread of wire, you bitch. Come on. It's 10% loss. It's really large. God damn it. What if I just like try and match the impedance here or something? If it's somewhere else, we're fucked. Did it work? No. Damn it. There are limits though for what it's worth. There are genuinely physics limits there. Of course, the cable changes its impedance and resistivity over a given distance as it moves and expands, heats up, and so on. Okay, so like you have to understand that, which then turns it into, instead of controlling the environment extraordinarily well, you then just basically set up like for the connector parts, like given variable dynamic changes to that for like it's basically like a capacitor, right? And so like it'll build up and make sure to properly match between each connector point. And so the given distance and change is still good and you get good acoustic resonances, right? But um still it's hilarious because it's like, yeah, no, it really upgraded so I made it specifically for silicon transistors initially because it was like I was having this issue with this they were like, this is a 96 core 128 thread or something, and I'm like, that's it only does this. I thought it had like terabytes a second, like hundreds of terabytes a second. It seems like 128 threads would do 100 like something terabytes a second. Is this not what it does? It's like kind of barely. What? What are you doing? And that was as a result of needing a really high speed analog camera. So it's a bunch of fiber optic points that I would essentially collect a bunch of little, wave frequencies, right? But then I would check from the side and down the line until the very end and have multiple different wavelengths that I could collect. but that meant I had a ridiculous number of dots, pixels, is what that would be really. But that means I get superposition, polarization, uh, pulses, and a whole bunch of other stuff, right? And like the way it started off as was like, this RAM can do this. Yeah, no, that's stupid. I'm not doing that. It needs to immediately go through an analog to this digital converter, which is essentially what it is. But it's like it goes into this RAM, but then the RAM needs to send it through the controller. The controller's like, I'm stupid and I'm programmed like this. I send the data in like this. That's dumb. Why would you do that? You have a closer to the RAM stick that it's connected to, and then further away Z depth, and then you have an inside and then towards the outside. So like the center of the chip towards the outside of the chip, right? And that's the binary it runs with. But it's like, that's dumb. Why would it do that the way it does? Because it like basically doesn't use that. It just sort of fills up wherever the hell it is. And it's supposed to know that. So there should be a constant talking between the two, and there should always be like like lowest Z depth to highest Z depth, and then it should go back down, and it should go from in out back towards in. So that way it can always know that, and then a half of it can always be deleting that to fill up that information, kind of like the snake game, where like you eat something and then you get a longer thing, but if you eat something it'll go lower, and if you have multiples, you have to fit in between. So it's like always timing intervals. And so it's like, if I'm deleting this, that means I now have more information that I could put there, while I'm also sending this information, which takes that as the bit it is, on through the analog to a binary, right, digital conversion, which means I can throughput it way faster. The problem is the controller needs to be a kernel program change, which I had to do to make that work. But that also meant that I had a much higher bandwidth than before, like by a few orders of magnitude. But that also means I broke my chips a lot. Like, it's not because they would overheat, they were cool. It's because they're not designed for that. I'm effectively shoving them, and then basically, like a battery, I'm charging and discharging them as fast as I can. Like, there's literally no other way to describe it other than I maxed out charge and discharge rates on a fucking chiplet for RAM. Which was like, oh, that's cool. But like, also, they're dead after like 3 minutes, essentially. And of course, that doesn't bode well for when you have to have that go through a buffer computer to then a actual computer server. So like that was a 32 core that eventually turned into a 64 core dual that would stick to a central like little plate like for the motherboard in the center, and then I would blow air through that and all that. But that means I have two of them in one chassis, and I had a bunch of fiber optic that would go into one side. That would then buffer it into a big NVMe storage that would then dump it onto the other side, which runs through a compression and detail catalog. No, sorry. It is categorization, filtration, detail, and then resolving, and then something else. Point is, what it meant is I got frames, I got different wavelengths, I got polarizations, I've got angles, lots of that, and all of them are all very, 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 very compressed, bare minimum amount of information that will break out with the uh, program I have for the server that would give me all of the information back. But that also meant I had to spend a buffer zone of like 700 terabytes or something. But I also chewed through in 3 minutes this massive, like 128 terabytes of DDR5 RAM. In 3 minutes, I went through the entire life cycle of RAM. Not hot, just discharge rates meant the cells were unusable. It wouldn't hold information anymore. It was gone. It's over. It's all she wrote. You can get used to it. But that also meant that the fiber optic, which was like, well, this is the type of laser and the sensor and the blah, 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 blah. So I went into their binary and was like, no, this is stupid. You could detect this, that, this, that. And it was like, no, I only have 100 gigabytes a second. Bullshit, you have 8 terabytes now. You can sense way more than this. Shut up. It's not even a joke. I know for a fact you can. You're going to fucking detect this, that, this, that, and this as changes that mean these types of binaries and bits. Then you're going to send it using this not being used currently chip on your bridge for the motherboard, which, by the way, is supposed to be for internet and like sending data to your RAM and or your hard drive storage, right? And it was like, go fuck yourself. You're doing this now. It became an analog. Like real quick, this digital device turns into an analog. It's like, this is the only fucking binary you have now. This is all you've got. I don't care if you're encrypted. You're not a chip I can't reprogram. Shut up. And it's like, same thing with the RAM and same thing with like the 32 core 64 thread. It's like, no, you're not. You're not that. You're not that at all. This is actually what you are. This is how many real threads you are. This is how many real all the things you really are now. These are your core packs. This is exactly what you mean when you go through this gate now. Instead of this math, you're doing this math. Shut the fuck up. Put it out as this. And I effectively broke their chips. Like realistically, it's like, no. I know binary machine and assembly language. It's like, I know you think you do this. This isn't what you do. I also know the physics of fucking basic electrical engineering, which means your phasing sine waves are not going to do this. This is actually what you're doing. Your power delivery now looks and works like this, which means you're going to do that. And I tested a little bit and all that, and it did it, and it worked. Right? It's just barely able to work. Just barely. I shit you not. I had yottabytes a second that I had to fucking deal with. And so, like, this doesn't really do that, but that's because I have 256 terabytes of DDR5 and a bunch more, like, throughput. So when I talk about it like that, it's like it goes in, it deletes it, it goes through this chip, it goes off to storage as fast as possible. That's that phasing and everything, and then like the first, instead of dimensional compression, it turns into this is actually just like a 1 and a 0, and then like storage wise here, and then it's all sequential effectively. And then it knows that because of this call to this and then this call to that. And so it's deleting it as it reads it over to this other one, and then it's filling everything it can as fast as possible, while then it's sending it and then compressing and categorize all that. So it's categorize, specification, detailing, filtration, and resolve, which with the 5 stages of this are. So thank you for the reminder on that, brain and all the rest that are remembering what I was doing. So I felt that, felt you. But what that means is I got 5 of these things that are attached to all of the data points for a given singular frame, but that one frame is actually this delta of time. But that one frame isn't really one frame. That one frame is actually this many analog signals over this amount of time. I was able to brute force a 250 or 128 terabytes, sorry, of DDR5 to yeet as much data through this analog. There's a little analog computer converter that makes it exceedingly possible, but also insanely not possible to deal with. Because it was like, no, tell me again about yottabots of fucking bullshit. And it's like, yes, guess what, fiber optic freaking PCIe card? You're getting a lot more upgrades here. You're not sending signals like this. I don't care what you said. This is actually how you pulse now. This is actually what your real wavelengths. You have this degree in variance and all this, and then all that crap basically. And it's like, no, 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 but actually what that really means is I made a liquid light pulsing multiple attosecond style. It's not really. It's not attosecond. I'm just letting people know it's not attosecond. It's very close though. I got to like very close to attoseconds. It would be like a couple, it'd be like 1,020 something uh attoseconds. So like not really actually attoseconds, but like whatever. But really it's like variances on the measurement of on the other side, which was a splitter. So I had, yeah, which isn't really, they're not called splitters, but they're routers or whatever, but or modem, whatever it is, right? But like that's, to me they're a splitter. This line in comes in and then like buffer it by sending multiple lines of fiber optic to multiple freaking servers and ingest, just fucking ingest, compress more fucking than it is. So comes in, tries a big petabytes of storage, right? But it's like, no, no, no. I need you to and then compress it into the top part, which is effectively the same storage amount, like the other one. There's a smaller one, but this one, it's like, no, no, no. There's no fucking way I'm storing all this. So it turned into, behold, my three of massive compression of just everything after a point, because it was like, no, 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 this is now 1 second, but it's actually not. It's technically speaking 10 seconds, but it's compressed like this, which now means it's not 1 second at all, except it'll break out into being chunks of insanely small amounts of time. We're talking picoseconds of measurement, okay? For light, right? Picoseconds, like genuinely picoseconds of light observational measurements. And a analog all the fucking like light from radio wave to gamma, because this one turned into, so radio wave oscillates blah blah blah, but if I curve it like this and then I filter it like this, then that changes into, these are multiple wavelengths of all radio wave in a small nano size capacity, effectively, for my fiber optics and my sensor stuff, which was great. I needed that. But I also needed gamma ray to be captured and not ionized stuff. So like gamma ray got converted to these particular polarization superpositional wavelengths that then collapsed into the type of tuning frequency that I was looking for my sensor, which is not apparently tuning frequency to some, but it's like it vibrates and makes electricity. I don't see what your issue is. So tuning fork electricity stuff, but it worked out. But anyways, I got to it and I got these yada bytes of bullshit for 3 minutes, right? But it's like, yeah, except not really. You run it once and then you have to replace everything. Except for like the actual big boy computer. Like the analog's good, but you have to always just, it's like that like you break open like the shotgun and then the shells come out. It's like dunk. Next thing you know, DDR5 is gone, and then like you place in more. Let's get going. We're doing more. It's not really. I didn't do that. Just FYI. But it was like that's the sense of like what that feels like, because it's that type of energy, that vibe. Like I'm fucking setting it up and I'm about to hit that trigger and then I have to replace everything. That really makes it work. But anyways, that's where that initial compression algorithm came from. So the categorization specification stuff, but then also multiple different like points of zeros are also ones and ones are also zeros, and then I was able to reference more and more if I take up a little bit more space for what that meant to the file type. And so if I layer that the right way, I was able to effectively get multiple, data points all to be referenced, even though that's like this file is referencing this thing, right? It's like that also over here means actually it's referencing this. And that eventually led to the dimensional part. So like eventually it was like dimension, how many dimensions can I put into a dimension? What? Probably infinite, right? No, not really. There's a limit here for sure. Because it needs to start from somewhere to be able to unravel, right? Right, yeah. So it's like how many and this is delta, and this is past, present, future, and then for this given type of, this reference and probability cloud, and it's just going to move fluidically, and I have this type of like to each one of the chiplets, and this type of, and this is what I can put onto its binary kernel system for its chip, for its controller, for its this, for this, and this will only work if it's these files that for my operating system that works exactly like this as a breakout hash algorithmic key, which can only do it correctly because it's completely encrypted as a result. So like literally you can't do it incorrectly and have anything that resembles something of anything. It's a bunch of random. But that's perfect. I know how to do that. But what that meant for everyone else was there was no fucking way I could read this except meanwhile me, well, there is a basic translator program to your C's and whatever DOSy that is. But it runs slower, obviously, because, it has to translate that, and it has to have that data table in that file type, but it'll work. It just takes a few seconds longer. Anyways, behold! 1,200 docellion bytes into 102 terabytes. That's right. 102 terabytes was what I sent to people, and it would work out as like a data, like you could scrub through it like an Adobe, that was the program or whatever, and like you could see it. And it's the real data, it's the raw data. It works out to the same. Like they were like, we're gonna see if in any way with our, stuff of file and operating system, if it's the same across all of yours and this one and that one. I'm paranoid, is what it felt like to me. But I was also like, yeah, but okay, but I kind of need the raw, so like I don't care. I need to process it way faster. So like, thanks for the decillion bytes a second. I'm gonna hook that up to my. But anyways, like it checks out. It was all the raw. It's the same exact data. It's exactly the same. I don't see why we needed the raw binary stored. But okay. But okay, right? They wanted it. They wanted the raw data. The unadulterated, there's no algorithm, there no, it's all error corrected, all that shit. And so they got it, whatever. But it was like, it's the same. There's no difference at all. But okay. Anyways, but that's basically what I use now for my God operating system. Like my God operating system is named aptly God operating system because it runs off the same way our analog and digital storage of our synaptic neural networks in our brain run. like how the protein and ionic exchange, so protein pumps that make a electrical current, but then also an ionic exchange elicits a greater increase of going this direction or that direction, or looping, continuing, or not. And field collapse is as well of charge. So there's charge fields, but then there's also electromagnetic field collapses, which create an increase of voltage capacities. Then there's gamma phase. Not well, there's that too, but that's rare. Okay, we're gonna move on from that for ionic exchanges, depending on what kind of food and so on that you're eating, because that gets into chemical persuasion moments of various processing in your brain. Right? There's a lot of stuff like that that go on uh effectively, very, very efficiently in our brain, right? And now, see, the reason why I was thinking about the reactors, like on a chip, is because it's like that's exactly how our brain works. It'll take an exchange and it'll recirculate it, like the electrical current type that I'm talking about. That's mine. Nobody else does it. So it's mine. That's right. There are practical examples, just mine, but it all works with physics. It passes logic check. Not mine, all of physics. If you know about it, I suppose. You'd have to be a smart brainiac, I guess. Hey, look at me. I'm putting a medal on my own fucking neck. I'm like Obama giving himself a medal. Hi there, brain. Hey, thanks. Anyways, if you're unaware, it's like, well, yeah, no, the reflective properties are great, but then it's more than just reflective properties. That forces greater degrees of electrical current, which also improves the likelihood chance of increasing the amount of electrons you get out of every neutron. But that means it's recirculating kind of like how our body does for cells. So like cell has ATP, which produces thermal, but also electrical, right? Potential. But actually, it's more of a bank for the mitochondria. It has multiple different exchanges that produce multiple different effects, right? Same for this, except it's very tightly controlled and more algorithmic in its construction, which means it really only has this input and it'll only have that output. So it's a battery, but it's a generator battery because more neutrons effectively come through, right? Like we're still next to a star and we still have charge variances in our atmosphere and we still move around, which means we generate some more electricity than what we would normally get. That's where it comes from, right? Which is fine. That's actually a good thing. You would want that for a battery in a nuclear reactor. A reactor or a generator of any kind only ever has so long for life, anyways. It's a-okay, but also it's now no longer going to have waste, which is the biggest part, and it's extraordinarily safe, which is the whole reason. And now I have hundreds of kilowatts in these tiny little pins I can send to people and their electric motors, which I described in that neutron thing as an electric motor type that I personally wanted to use that's extraordinarily efficient. It doesn't generate heat. It doesn't need much in terms of a controller. It still needs to have a controller, but it also needs to impedance match and all that. But it works really rather well as a result of that. And so this is a really good direct one-to-one conversion, which can decarbonize our entire industry with nuclear physics. But I also have a lot of other ones. So, anyways, please like and subscribe. Also, ring that bell for notifications. Share, please. I'm trying to grow. Yeah, have a good one. Bye.